This is Group A-03B's project report. Our cart can be broken down into two separate systems. The first system is a cart rolling down an inclined plane. It can be modeled as a mass sliding down a frictionless plane. The negligible forces are rotational inertia, air resistance, friction within bearings, and rolling resistance. Our cart had a final mass of 1.35 kilograms. Our second system is a braking device. The braking device consists of a servo pressing a metal ruler into the wheel. The amount of normal force applied by the ruler is equal to the amount of deflection by the servo. The servo treats the ruler as a supported beam. The force of the ruler was characterized by applying known masses to the end and measuring the deflection. The servo is characterized by the time taken to reach the angle of deflection approximated as a linear first-order system. The torque from the ruler spring system affects the speed. The free speed and stall speed was found with the servo datasheet. The coefficient of friction between the ruler and the wheel was determined by placing the two materials in contact and slowly raising the angle of the ruler until the rubber band material began sliding at a constant rate. The tangent of this angle is equal to the kinetic coefficient of friction. The following video is a demonstration of the braking system in action. The controller requirements were to slow the cart to the desired speed in a safe and controlled manner and to minimize the steady-state error in large overshoots. In order to meet these requirements, we selected to have the limitations be a plus and minus 10% of the target speed, a maximum of 20% overshoot of the target speed, and a 10% settling time of 3 seconds after the controller becomes active. A PID controller was used to give flexibility to tune the system. Looking at the resulting plots of the trials, we can tell that noise is an artifact of the encoder's angle reading. The encoder was outputting a signal varying about 3 degrees even when still. All attempts to find a solution were unsuccessful, so a moving average was added to the Arduino's code to yield smoother data. You will also notice that there is a simulated versus simulate time-shifted curves data points on the plots. The shift is necessary because of the buffer zone in the code controlling the speed. This prevents control when the cart is stationary, and it prevents complete stops from happening. The buffer region was not active during the entire time interval. Lining up the data so that the speeds cross where the controller begins to brake results in a relatively close alignment. Finally, the final controller gains were a KP of 13, a KI of 15, and a KD of 1. This project successfully showcased the design, simulation, and implementation of a PID control system for managing the speed of a cart rolling down an inclined plane. Overall, the project provided valuable insight into feedback control design and implementation.